1. Which of the following return type cannot be used for a function in C? A. Char asterisk. B. Struct. C. Void. D. None of the mentioned. Answer D. Explanation. In the C programming language, various data types are used to specify the type of data that a function returns. Here are some commonly used return types in C. 1. Void. This return type indicates that the function does not return a value. It is typically used for functions that perform actions or tasks without returning any result. 2. Int. The int return type is used when a function returns an integer value. It can represent both positive and negative whole numbers. 3. Float. The float return type is used when a function returns a floating point value. It represents single precision floating point numbers. 4. Double. The double return type is used when a function returns a double precision floating point value. It can represent higher precision floating point numbers compared to float. 5. Char. The char return type is used when a function returns a single character value. 6. Pointer types. Functions in C can also return pointer types. These can include pointers to various data types, such as int asterisk, float asterisk, char asterisk, or void star. 7. User-defined types. C allows defining custom data types using structures or typedef. Functions can also return these user-defined types. It's important to note that C does not support returning arrays directly. However, you can return a pointer to an array or use structures to encapsulate arrays and return the structure. These are some of the common return types in the C programming language. The appropriate return type depends on the specific data that the function needs to return. Next question. To a system wherein items are added from one and removed from the other end. A. Stack. B. Queue. C. Linked list. D. Array. Answer B. Explanation. The system you are describing is commonly known as a queue. In a queue, items are added to one end, called the rear or tail, and removed from the other end, called the front or head. This type of behavior is often referred to as first in first out, FIFO. In programming, queues can be implemented using various data structures, such as arrays or linked lists. Here is a brief overview of the operations commonly associated with a queue. 1. Enqueue, adding an item to the rear tail of the queue. 2. Dequeue, removing an item from the front head of the queue. 3. Peek, examining the item at the front head of the queue without removing it. 4. IsEmpty, checking if the queue is empty. 5. Size, determining the number of items currently in the queue. The enqueue operation adds an item to the rear of the queue, while the dequeue operation removes an item from the front of the queue. The peek operation allows you to look at the item at the front of the queue without removing it. Queues are commonly used in various applications, such as process scheduling, task management, and message passing between different components of a system. Next question. 3. Array is preferred over linked list for the implementation of underscore. A. Radix sort. B. Insertion sort. C. Binary search. D. Polynomial evaluation. Answer C. Explanation. Arrays are generally preferred over linked lists for the implementation of binary search due to the following reasons. 1. Random access. Arrays provide constant-time random access to elements based on their indices. Binary search relies on accessing elements in the middle of a sorted collection, which can be efficiently achieved using array indices. Linked lists, on the other hand, require traversing the list from the beginning to reach a specific index, resulting in slower access time. 2. Cache performance. Arrays exhibit better cache performance compared to linked lists. Modern computer architectures are designed to optimize memory access patterns. Arrays offer better locality of reference, as elements are stored in contiguous memory locations. This allows for more efficient caching and reduces cache misses, resulting in faster access times. Linked lists, on the other hand, store elements at arbitrary memory locations, making cache management less efficient. 3. Memory efficiency. Arrays generally require less memory overhead compared to linked lists. Linked lists require additional memory to store the pointer's references for each element, which can increase memory consumption. Arrays only need memory for the actual elements, resulting in more memory-efficient usage. 4. Search space division. Binary search involves dividing the search space in half at each step. This process is more straightforward and efficient with arrays because they provide constant time access to midpoints using index calculations. In linked lists, dividing the search space requires traversing the list, resulting in a less efficient process. However, it's important to note that arrays have a fixed size, whereas linked lists can dynamically grow or shrink in size. So if the size of the collection is not known or can change frequently, and efficient insertion or deletion of elements is required, a linked list might be a more suitable choice despite the mentioned disadvantages for binary search. Next question. 4. Calloc. Initialize memory with all bits set to 0. A. True. B. False. C. Depends on the compiler. D. Depends on the standard. Answer. A. Explanation. The calloc function in C initializes the allocated memory block with all bits set to 0. This behavior is defined by the C language specification and serves several important purposes. 1. Consistent initialization. By setting all bits to 0, calloc ensures that the allocated memory is consistently initialized, regardless of the underlying representation of data types. This means that all bytes within the allocated block will be initialized to 0 values, providing a predictable starting point for subsequent operations. 2. Avoiding garbage values. When memory is allocated using malloc, or similar functions, the contents of that memory block are typically undefined and can contain arbitrary values, commonly referred to as garbage values. Initializing the memory with zeros using calloc prevents the presence of these unpredictable garbage values, ensuring a known and reliable state for the allocated memory. 3. Useful for initialization. Setting all bits to 0 is often useful when initializing variables, arrays, or data structures. It provides a default or initial state that can be easily recognized and handled by the programmer. For example, an array initialized with zeros is equivalent to setting all elements to their default values. 4. Ensuring compatibility. Zero initialization of memory is also important for ensuring compatibility across different systems and architectures. In some cases, Certain platforms or data types may rely on zero-initialized memory to work correctly. By adhering to the standard behavior of calloc, code can be written in a portable manner without relying on specific platform-dependent behaviors. It's worth noting that calloc also takes the number of elements and the size of each element as parameters, allowing for easy allocation and initialization of arrays or structures. Next question. 5. Can the break statement be used to abort a program? A. Yes. B. Yes, but only if it is used within the global scope. C. No. D. Yes, but only for some Arduino boards. Answer. C. Explanation. No, the break statement in C cannot be used to abort a program. The purpose of the break statement is to exit a loop prematurely, such as a for loop, while loop, or switch statement. When encountered, the break statement terminates the innermost loop or exits the switch statement, allowing program execution to continue from the next statement after the loop or switch block. If you want to abort a program completely and exit it before reaching the normal end, you can use the exit function. The exit function is defined in the stlib.h header file and allows you to terminate the program and return a status code to the operating system. Here is an example of how to use the exit function to abort a program in C language. #include stlib.h int main program code. If condition exit 0, abort the program. Program continues. Return 0. In the example, if the specified condition is met, the exit 0 statement is executed, terminating the program immediately. The 0 passed as an argument to exit represents a successful termination, and you can use different values to indicate different exit statuses if needed. It's important to note that when the exit function is called, any open files or allocated memory are automatically cleaned up by the operating system, and the program terminates abruptly. Next question. 6. Choose the statement which is incorrect with respect to dynamic memory allocation. A. Memory is allocated in a less structured area of memory, known as heap. B. Used for unpredictable memory requirements. C. Execution of the program is faster than that of static memory allocation. D. Allocated memory can be changed during the runtime of the program based on the requirement of the program. Answer. C. Explanation. In general, it is true that the execution of a program using static memory allocation can be faster than that of dynamic memory allocation. Static memory allocation refers to the allocation of memory at compile time, where the size and structure of the data are determined in advance. Here are some reasons why static memory allocation can be faster. 1. No runtime overhead. With static memory allocation, memory is allocated once during program initialization. There is no overhead associated with runtime allocation or deallocation, as the memory is fixed and does not change during program execution. 2. Efficient memory access. Static memory allocation allows for efficient memory access because the memory is contiguous and can be directly accessed using memory addresses or pointers. This results in faster memory operations and reduces cache misses, improving overall performance. 3. Predictable memory usage. Since the memory allocation is determined at compile time, the memory requirements are known in advance. This allows for more efficient memory management and optimizations during compilation, leading to potentially faster code execution. However, it's important to note that dynamic memory allocation provides flexibility and is necessary in many scenarios. Dynamic memory allocation allows for data structures to grow or shrink at runtime and enables more efficient memory utilization when dealing with variable-size data or complex data structures. In certain cases, dynamic memory allocation can be faster or more efficient, especially when dealing with large or dynamically changing data structures. However, it comes with the overhead of runtime memory management and can potentially lead to issues such as memory fragmentation or leaks if not managed properly. In summary, while static memory allocation can offer performance benefits in terms of faster access and predictable memory usage, the choice between static and dynamic memory allocation depends on the specific requirements of the program and the nature of the data being processed. Efficient memory management and overall program design play a significant role in achieving optimal performance. Next question. 7. Comment on the following two arrays with respect to P and Q. 1 int asterisk a1, 8, 2. Int asterisk a2, 8, 3. P array of pointers 4. Q pointer to an array. A1 is P, a2 is Q. B, a1 is P, a2 is P. C, a1 is Q, a2 is P. D, a1 is Q, a2 is Q. Answer, B. Next question. 8. Comment on the following C statement. N is equal to 1. Printf, %d, %dn, 3 asterisk n, n plus plus. A. Output will be 3, 2. B. Output will be 3, 1. C. Output will be 6, 1. D. Output is compiler dependent. Answer, D. Explanation. The given C statement is C. N is equal to 1. Printf, %d, %d backslash n, 3 asterisk n, n plus plus. This statement consists of two parts, assignment, n is equal to 1, and a print statement, printf, %d, %d backslash n, 3 asterisk n, n plus plus. One assignment, n is equal to 1. This line assigns the value 1 to the variable n. It sets n to be 1. To print statement, printf, %d, %d backslash n, 3 asterisk n, n plus plus. The printf function is used to print formatted output to the console. The format string, %d, %d backslash n, specifies that two integer values will be printed, separated by a comma and followed by a new line character. Inside the printf function, there are two arguments, 3 asterisk n and n plus plus. 3 asterisk n represents the result of multiplying the value of n by 3. N plus plus represents the post-increment operation, which increments the value of n by 1 after it has been used in the expression. However, it's worth noting that the behavior of the n plus plus operation within the printf statement leads to undefined behavior. According to the C language specification, modifying a variable more than once between two sequence points, without a sequence point in between, results in undefined behavior. In this case, The value of n is being modified both in the n++ operation and through the 3*n expression without a sequence point in between. The result could vary depending on the compiler and platform, and it is best to avoid such code to ensure predictable behavior. To avoid the undefined behavior and achieve predictable results, it's recommended to modify the code to separate the increment operation from the expression being used in the printf statement. For example, n is equal to 1. Int temp is equal to n++, separate the increment operation. Printf, %d, %d\n, 3*temp, n. In this modified version, the increment operation n++ is separated into a separate variable temp, ensuring well-defined behavior.
Next question. 9. Comment on the following C statement.
Const int *ptr.
A. You cannot change the value pointed by ptr. B. You cannot change the pointer ptr itself. C. You may or may not change the value pointed by ptr. D. You can change the pointer as well as the value pointed by it. Answer, A. Explanation. No, you cannot directly change the value of ptr in const int *ptr, because the const qualifier indicates that the pointed to data is read-only. It signifies that the variable being pointed to is constant, and any attempt to modify it through the ptr variable would result in a compilation error. Consider the following example. C. Const int *ptr. Int number equals 10. Ptr equals end number, // valid, pointer to a constant integer. Asterisk number equals 20, // invalid, attempting to modify a const int through ptr. In the example, ptr is a pointer to a constant integer, denoted by the const int * declaration. It is pointing to the variable number, which is declared as a regular int. However, since ptr is declared as a pointer to a const int, any attempt to modify the value of number through ptr will result in a compilation error. If you want to be able to modify the value being pointed to by ptr, you would need to remove the const qualifier from the declaration. For example, int *ptr. Const int number equals 10. Ptr equals end number, // warning, discarding const qualifier. *ptr equals 20, // valid, modifying the value through a non-const pointer. In this case, ptr is a pointer to a non-constant integer, allowing you to modify the value of number through ptr. However, note that in this example, we assign the address of a constant variable number to a non-const pointer ptr, which discards the const qualifier. This may lead to potential issues or unintended behavior, so it's important to be cautious when modifying variables that are originally declared as const. Next question. 10. Comment on the following C statement.
Int *a 7.
A. An array A of pointers. B. A pointer A to an array. C. A ragged array. D. None of the mentioned. Answer, B. Explanation. The C statement int *a 7 declares a pointer A to an array of integers with 7 elements. Here's a breakdown of the statement. Int specifies the data type of the elements in the array, which is int. *A declares a pointer variable named a. 7 specifies that the pointer a points to an array with 7 elements. In other words, a is a pointer that can hold the address of an array of integers with 7 elements. The parentheses around *a are necessary to indicate that a is a pointer and not an array itself. This type of declaration is useful when you want to create a pointer that can point to a specific array size or when dealing with multi-dimensional arrays. For example, int *7 can be used to point to an array of integers with 7 elements, and you can access and manipulate the elements of the array using pointer arithmetic or array indexing. Here's an example demonstrating the usage of such a declaration. Int main. Int arr7 equals 1, 2, 3, 4, 5, 6, 7. Int *a 7 / declare a pointer to an array of 7 integers. A equals and arr / assign the address of the array to the pointer. / access and print the elements using pointer arithmetic. 4. Int I equals 0, I7, I++. Printf, %d, a plus I. Printf, \n. Return 0. In the example, a is declared as a pointer to an array of 7 integers. It is assigned the address of the arr array, allowing us to access the elements of arr through a. Using pointer arithmetic, we can dereference a and access the individual elements of the array. Keep in mind that this declaration does not allocate any memory for the array itself but allows you to manipulate an existing array using a pointer. Next question. 11. Comment on the following pointer declaration.
Int *ptr, p.
A. ptr is a pointer to integer, p is not. B. ptr and p, both are pointers to integer. C. ptr is a pointer to integer, p may or may not be. D. ptr and p both are not pointers to integer. Answer, A. Explanation. The pointer declaration int *ptr, p, declares a pointer ptr to an integer and a regular integer variable p. However, there is a potential ambiguity in this declaration that may lead to unintended behavior. Here's a breakdown of the declaration. Int *ptr declares a pointer variable named ptr that can hold the memory address of an integer. P declares a regular integer variable named p. At first glance, it may appear that both ptr and p are pointers to integers. However, due to the way the declaration is written, only ptr is a pointer, and p is a regular integer variable. To clarify the intention and avoid potential issues, it's recommended to declare each variable on a separate line. Int *ptr. Int p. With this modified declaration, it is clear that ptr is a pointer to an integer, and p is a regular integer variable. Additionally, when declaring multiple variables in a single line, it's good practice to initialize them explicitly to avoid uninitialized variable issues. Int *ptr equals null. Int p equals 0. Initializing the pointer ptr to null and the integer p to 0 provides initial values and helps prevent accessing uninitialized memory. By following these practices, you can avoid confusion and ensure the intended types and initializations of your variables. Next question. 12. The word underscore 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 comes from the name of a Persian mathematician Abu Ja'far Muhammad ibn Musa al-Khwarizmi. A. Flowchart. B. Flow. C. Algorithm. D. Syntax. Answer, C. Explanation. The word algorithm comes from the name of a Persian mathematician Abu Ja'far Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi, who lived during the 9th century, made significant contributions to mathematics and is often considered the father of algebra. His name has been Latinized as algorithmi, which eventually evolved into the term algorithm used today. Al-Khwarizmi's work on mathematical techniques and problem-solving methods had a profound influence on the development of modern mathematics and computer science. Next question. 13. How do you initialize an array in C? A. Int arr3 equals 1, 2, 3. B. Int arr3 equals 1, 2, 3. C. Int arr3 equals 1, 2, 3. D. Int arr3 equals 1, 2, 3. Answer, C. Explanation. In C, you can initialize an array during its declaration using several methods. 1. Initializing with values enclosed in braces. Int arr equals 1, 2, 3, 4, 5. In this method, the size of the array is automatically determined based on the number of values provided within the braces. 2. Initializing with specific values and size. Int arr5 equals 1, 2, 3, 4, 5. In this method, the size of the array is explicitly specified as 5, and the provided values are assigned to the corresponding array elements. 3. Partial initialization with remaining elements initialized to 0. Int arr5 equals 1, 2. In this method, the first two elements of the array are initialized with 1 and 2, respectively, while the remaining elements are automatically initialized to 0. 4. Initializing with designated initializers, C99 and later. Int arr5 equals 1 equals 10, 3 equals 20. In this method, specific elements of the array can be initialized using designated initializers, where the indices are specified within square brackets. 5. Initializing with a single value, which is applied to all elements. Int arr5 equals 0. In this method, all elements of the array are initialized with the value 0. It's important to note that when initializing an array, the number of elements provided should not exceed the size of the array. If the provided values are fewer than the size of the array, the remaining elements are automatically initialized to 0, for numeric types, or a null character, \0 for character arrays. Additionally, it is also possible to initialize arrays dynamically at runtime using loops or by assigning values to individual array elements after declaration. Next question. 14. How is search done in #include and #include some library.h according to C standard? A. When former is used, current directory is searched, and when latter is used, standard directory is searched. B. when former is used, standard directory is searched, and when latter is used, current directory is searched. C. When former is used, search is done in implementation-defined manner, and when latter is used, current directory is searched. D. For both, search for some library is done in implementation-defined places. Answer, B. Explanation. According to the C standard, the hashtag include directive is used in C programming to include header files, which provide declarations and definitions for functions, types, and other entities used in the program. When the preprocessor encounters an hashtag include directive, it searches for the specified header file in a predefined sequence of locations. 1. The current directory. The preprocessor first looks for the header file in the same directory as the source file that contains the hashtag include directive. If the header file is found in the current directory, it is included. 2. Compiler-specific include directories. The preprocessor searches in a set of directories specified by the compiler, commonly known as include directories. These directories typically contain standard library headers and other commonly used headers. The order and specific directories searched may vary depending on the compiler and platform. 3. Standard system directories. If the header file is not found in the current directory or the compiler-specific include directories, the preprocessor searches in the standard system directories. These directories contain system-specific header files provided by the operating system or development environment. The method of specifying header file paths in hashtag include directives can vary depending on the usage of angle brackets, or double quotes. Hashtag include header.h. This syntax is typically used to include standard library headers. The preprocessor searches in the compiler-specific include directories and standard system directories. Hashtag include header.h. This syntax is commonly used to include user-defined or project-specific headers. The preprocessor first searches in the current directory, and if the file is not found, it continues to search in the compiler-specific include directories and standard system directories. It's important to ensure that the necessary header files are included correctly to provide the required declarations and definitions for the program. Incorrect inclusion or missing headers can lead to compilation errors due to undefined symbols or undeclared functions. Next question, 15. How many number of pointer, asterisk, does C have against a pointer variable declaration? A. 7. B. 127. C. 255. D. No limits. Answer, D. Explanation. In C, a pointer variable declaration can have one or more asterisks, asterisk, depending on the level of indirection or the complexity of the pointer. Here are a few examples to illustrate the different cases. One single level pointer. Int asterisk ptr. In this case, ptr is a single level pointer that can hold the memory address of an integer. 2 double level pointer. Char ptr. Here, ptr is a double level pointer, also known as a pointer to a pointer. It can store the address of a pointer variable that, in turn, holds the address of a character variable. 3 triple level pointer. Float ptr. In this example, ptr is a triple level pointer, which can store the address of a double level pointer that, in turn, holds the address of another pointer variable that finally points to a float value. The number of asterisks, in a pointer variable declaration corresponds to the level of indirection required to access the underlying data. Each additional asterisk represents another level of indirection or another layer of nested pointers. It's important to note that while there is no theoretical limit to the number of levels of indirection in a pointer, it's generally recommended to keep the pointer complexity to a manageable level for code readability and maintainability. In most cases, single-level or double-level pointers are sufficient for common programming scenarios. Next question. 16. How many times is a printed when the following C code is executed?
#interlude stdio.h main int a is equal to f1 10 printf %d a f1 int b if b is equal to 0 return 0 else printf a f1 b
A. 9 times. B. 10 times. C. 0 times. D. Infinite number of times. Answer, D. Explanation. In the given C code, the letter A is printed multiple times. However, there is an issue with the code that leads to an infinite recursive loop. Let's analyze the code and understand the behavior. #include stdio.h f1 int b if b equals 0 return 0 else printf a f1 b int main int a equals f1 10 printf %d a return 0. The function f1 is a recursive function that prints the letter A and calls itself with b decremented by 1. The recursion continues until b reaches 0, at which point it returns 0. However, there is an error in the recursive call f1 b. The post-decrement operator b does not immediately decrement b, instead, it evaluates the expression and then decrements b. So the value passed to the recursive call is still the original value of b, resulting in an infinite recursion and an infinite printing of it. To fix the code, you can change f1, b, to f1, b, 1, to correctly pass the decremented value to the recursive call. f1, b, 1. With this modification, the code will print the letter A 10 times and then terminate. Next question. 17. In the absence of an exit condition in a recursive function, the following error is given _________________________________________ A. Compile time error. B. Runtime error. C. Logical error. D. No error. Explanation. In the absence of an exit condition in a recursive function, the program will not terminate and can lead to a runtime error called stack overflow or stack exhaustion. This error occurs when the recursion consumes all available space on the call stack, which is a limited resource. When a function is called recursively, the program pushes information, such as return address and local variables, onto the call stack to keep track of the function calls. If there is no proper exit condition to break out of the recursion, the stack continues to grow indefinitely, eventually exceeding its capacity. When the call stack overflows, it results in a Stack Overflow error, which typically leads to a program crash or termination. The exact error message may vary depending on the programming language and environment. To avoid this error, it's crucial to ensure that recursive functions have a proper exit condition that eventually terminates the recursion. The exit condition should be based on the problem being solved or a specific condition that indicates the end of the recursive process. Next question. 18. In the following C code, we can access the first character of the string sval by using underscore 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 underscore.
Hash include stdio.h struct char asterisk name union char asterisk sval u simtab 10
A. Asterisk simtab i.u.sval. B. Simtab i.u.sval 0. C. You cannot have union inside structure. D. Both asterisk simtab i.u.sval and simtab i.u.sval 0. Answer, D. Explanation. In the given C code, you can access the first character of the string sval in the simtab array using the following methods. Method 1, using the array subscript operator and indexing with 0. Simtab index.u.sval 0. This method directly accesses the first character of the string sval by indexing it with 0. Method 2, dereferencing the pointer and accessing the character. Asterisk, simtab index.u.sval. This method dereferences the pointer simtab index.u.sval to obtain the first character of the string. Both methods allow you to access the first character of the string sval stored in the simtab array at the specified index. Next question 19.
In the following code snippet, character pointer str holds a reference to the string underscore 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 underscore. Char asterisk str is equal to Indian Tech Guru in \0 training classes.
A. Indian Tech Guru in. B. Indian Tech Guru in \0 training classes. C. Indian Tech Guru in training classes. D. Invalid declaration. Answer, B. Explanation. In the given code snippet, the character pointer str holds a reference to the string Indian Tech Guru in \0 training classes. The string being referenced consists of two parts that are concatenated together. 1. Indian Tech Guru in \0. This part of the string ends with the null character \0, which is used to terminate C-style strings. The presence of \0 indicates the end of the string. 2. Training classes. This part of the string is concatenated to the first part without any separation. When the two string parts are concatenated together, the resulting string is Indian Tech Guru in \0 training classes. Note that the null character \0 is treated as part of the string but is not included when the string is printed or processed using string functions. So, the character pointer str holds a reference to this combined string. Next question. 20 local variables are stored in an area called underscore 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 underscore. A. Heap. B. Permanent storage area. C. Free memory. D. Stack. Answer, D. Explanation. Local variables in C are stored in an area called the stack or stack memory. The stack is a region of memory used by programs to manage function calls and local variables. When a function is called, its local variables are allocated on the stack, and when the function returns, the stack memory is reclaimed for future use. Each function call typically creates a new stack frame, which contains the local variables and other information specific to that function call. As the function returns, the stack frame is popped off the stack, and the memory is freed. The stack operates in a last-in first-out (LIFO) manner, meaning that the most recently added stack frame is the first to be removed when functions return. Local variables stored on the stack have a limited lifetime within the scope of the function in which they are defined. They are automatically allocated and deallocated as the program flows in and out of the function's execution.